All right, we're going to do this problem. You can find it in your textbook on page 646. It's problem number 58. All right, if you take a look at problem number 58, it says at a particular temperature, K is equal to this value for the reaction below. In an experiment, 1 mole of N2O4 is placed in a 10-liter vessel. Calculate the concentrations of N2O4 and nitrogen dioxide when this reaction reaches equilibrium. All right, so what I've done is I've rewritten this equation right here with the Kc. And to get the 0.1 molar, remember molarity is moles per liter. And it was 1 mole per 10 liters, which equals 0.1 molar. All right, that's how we got the original concentration over here. They gave us no concentration of this for our initials. Now, you know, the first step to do then is to make sure that you write a K expression. So I'm going to write my K using NO2 squared over N2O4, right? To paying attention to the stoichiometry. We know that when there's nothing over here, that this is going to have to make some of that. So I'm going to remove some of this to make some of that. Don't forget to always look at that stoichiometry in the balanced equation. So you look at that stoichiometry twice, right? When you write your K expression and also when you're writing your X's. The E, which we call equilibrium little equations, I combine the I and the C together, and I'm just bringing this down. All right. So the E is going to be placed into here, but I want to see whether or not I can make that assumption to ignore the X. Remember, this is a really small K. That means that I will have most of the concentration on the reactant side and just a tiny little bit over here on the product side. The majority is found over here. So even though some of this has to be made into the product, I am going to assume that such a little amount is actually going to be removed from here that it's not even going to impact the 0.1 molar solution I'm starting with. I'm assuming I'm going to have a very, very, very small concentration over here because that's what the small k is telling us. So I'm going to ignore this x. I'm making my assumption. I'm going to write those e values where they belong in your k expressions. So this is 2x squared now, 0.1 molar by itself. All right. Now I'm going to do the math. And by doing this math, I'll have 4x squared over 0.1 is equal to 4 times 10 to the negative 7. All right, you have all finished that to determine what the x is. So pause this and do the work on your own. You should get a value of x squared equals 1 times 10 to the negative 8, so that the x is 1 times 10 to the negative 4th. That's my final value for x. I have to do the 5% rule because I've made an assumption, so that's equal to c over I. I'm only interested in the column where I made that assumption. So remember, I'm going to take the absolute value, which is x divided by 0.1 times 100. I'm going to put the x value where it belongs in here. So this becomes 1 times 10 to the negative 4 over 0.1 molar times 100 to get it into a percent. And I get 1 times 10 to the negative 1% or 0.1%. All right, I think that's easy to say that it's less than 5%. So my assumption was good. So because that's good, now I can calculate my equilibrium concentrations. So I'm going to look at the N2O4, which is 0.1 minus x. That is such a small x that that's not even going to impact the 0.1 molar. So I'm going to say it's essentially 0.1 molar. And then my concentration of NO2, according to the E, is a 2x. Put my x value where it belongs. And this becomes 2 times 10 to the negative 4th molarity. Remember, we made this assumption because it was a small k, that most of it was going to stay on the reactant side. Very little was going to be made on the product side. And I believe at the very end it shows you very little product was made. Most of it is the reactant.